Okay, for those that are not slide in the attendance yet, after this, at the end of this lecture, I will show again the QR code. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to all of you. So today we proceed with second lecture of uh, SKEU, Principle of Communication, and today we will learn about the second part of introduction, that is noise. So as you know, I already shared the homework related to noise in the e-learning, that you need to do the mind map. Okay, some of you already submitted it. Thank you so much. So for this mean that that homework is related to the part of this lecture, so I will go fast for that part because you already learn from the article and you already do the homework, do the mind map. So I hope that you already understand about the introduction to the noise, what is the noise, internal and external noise, and related to the noise. So okay. Okay, today motivational quote is put your heart, mind and soul into even smallest act. This is the secret of success. Okay, so whatever you do, do with full-hearted. Okay, so recap last lecture. So you already learned about the what is communication system, history of communication system, regulation related to communication system, type of signals, process in communication system, type of communication, components of communication system, modulation process, efficiency of communication system. So actually you already learned many things, and I already assessed you in quiz last week quiz. So 11 of you got the full mark. So Alhamdulillah, hopefully you understand well for the first lecture, but some of you still got 5 mark. So for those that got low mark for the quiz, you should go again to the slide and make sure you understand about the first lecture. So today you will learn about noise in communication system and formula of noise. There are more formula of noise. So be ready with your calculator. Okay, so noise in communication is the unwanted signal, random signal that exists in communication system. So you already learned this through article that I share for the homework for the mind map. So I explain more on this. So the effect of the noise degrade the system performance, face difficulty to understand the original signal, reduce the efficiency, then the signal may distort the information carried by the signal. So hopefully you understand well for the introduction of the noise through the article that I already give you for the homework. So yes, like that this one, there are two sources of noise in communication system, the external noise and internal noise. So for the external noise is interference outside of the device, either man-made or natural resources. There are lightning, solar noise, crosstalk and many more in the article that I share to you. And for the internal noise, it's within the device. So it's include the thermal noise or Johnson noise. The thermal noise is caused by the random movement of electrons within a conductor due to thermal agitation, because there are electron in the conductor. So the movement of electron caused by the thermal increase will cause the noise. And the other one is short noise. Short noise is random arrival of carrier, electron and holes at the output element of an electronic device, for example, diode. So for thermal, it's about movement, and for the short, it's about arrival of the carrier. So for this current noise, I focus on the internal noise. Okay, so thermal noise is the electronic noise generated by the thermal agitation of the charge carrier, the electron inside the electrical conductor in equilibrium, which happen regardless of any applied voltage, because the movement of the electron will form kinetic energy in the conductor related to the temperature of the conductor. And when the temperature increase, the movement of the free electrons will increase in the current flow through the conductor, and the current flow due to the free electron will create noise voltage. So this noise voltage will is influenced by temperature, and therefore it's called thermal noise. So thermal noise, also known as Johnson noise or white noise or Nyquist noise. So if you see in the question is asked about white noise, it actually a thermal noise. So the formula for the Johnson or Nyquist noise is, because the thermal noise was first measured by Johnson B. Johnson in 1928. He described his finding to Harry Nyquist. So there are two persons, Johnson and Nyquist. So this formula called Johnson-Nyquist formula. So they found that noise power generated is proportional to the temperature. So it's the formula is P proportional with the TB. So this is the formula that they found. P proportional to the temperature, and bandwidth. BW is bandwidth. So when it is proportional, it's come into constant. So K is constant, Boltzmann constant. So the formula for noise is P equal to KTB, where the K is the Boltzmann constant. The value is 1.38 times 2000 times 10 power of negative 23. So you need to remember this value for K. And T is temperature, but temperature measure in Kelvin. So if the temperature given in Celsius, you need to plus 273. So for Celsius. So it's become Kelvin. So this is in the Kelvin unit. And B is the bandwidth spectrum with the unit Hertz. So P equal to KTB. And the noise power can be modeled by using voltage equivalent circuits, Thevenin equivalence circuit. So if you have Rn and Vn, so here is RL. So if the here is the V here, the equation is RL over Rn plus RL. Rn is here. Rn plus RL times Vn. Vn is here. This is Vn. So because the Rn equal RL equal R, so it's become Vn over 2. Can you see here? Vn over 2. So so VL equal Vn over 2, Vn over 2, and then okay, so can you see? Okay, so the okay, so we have VL equal to Vn over 2, and then equation for the power is VL square over R, because P equal IV. Okay, P PL equal to VL square over R, and okay, this is the equation for P, and then VL is here. VL equals Vn over 2. So substitute the Vn over 2 into the equation of VL here, and then you will get the equation is Vn squared over 4R. So okay, and then P equals to KTB. So Vn squared over 4R equal to KTB. So you will get the equation is Vn squared equal to 4 KTBR. You put this bottom part into the right part. So Vn squared equal to 4 KTBR, or Vn equal square root of 4 KTBR. Okay, this is the equation. So you need to remember the equation of P equal to KTB, and then V squared or Vn squared equal to 4K TBR or 4R KTB. So you need to remember this, jot down in your notebook. Okay, so try this example first. This example, use the previous equation.
Doktor,
Yes.
yang untuk bandwidth tu kita nak guna nilai 18 ke 20 tu ke?
18 to 20 ialah 18 minimum, 20 maksimum. Okay, cuba fikir bandwidth dia berapa?
Kena ambil antara tu lah.
Tolak, yes. 20 tolak 18.
Okay.
And then make sure that the unit is hertz only. So this is megahertz. You need to change into 10 power of 6. That means 2, the bandwidth is 2 times 10 power of 6 for the mega. Okay, ada anyone that get the answer? Okay, or maybe some of you can try and show with us, or just share the value that you got. Atira, can you solve the problem?
Yes.
Okay, what's the V value that you got?
I get 8.28 to the power of negative 15.
8?
8.28
Okay, what formula that you use?
P equal to KTB.
P equal to KTB.
Yes.
That's this one is voltage. So you need to use the square root. That's mean V square root, V squared equal to 4R KTB.
Okay.
Okay, so try use that equation first. Okay,
Yes.
anyone that already try, can you share with us your answer? So we will discuss, and if you got wrong, so we can discuss what is that's mean how to solve it the right one. Afika?
Doctor,
Yes.
Doctor, I want to ask, what is
Rehan.
K? K is what? What value?
K is 1.38 to power of 10. Okay, this one.
Okay, Doctor.
1.38 times 10 power of negative 23. Okay, Natasha Amira, you got. Where is the chat? Okay, Natasha Amira, what you got the answer? I show your answer in the chat room, but it's gone. I don't know how to check it again.
1.820 to the power of 10 negative 5 voltage.
Okay, yes. So 1.8 power of 10 power of negative 5 or 18 microvolts. So you use the equation, this one. V squared equal to 4 KTBR, and then you will got V is square root of this one. So anyone that have problem to get the answer? The answer is 18 Okay, this is the answer. So for is the okay for KTBR, the K is this one is the K, and T is in Celsius, so you need to change to Kelvin. So plus 275. Okay, this is the bandwidth. It show the range, and then you need to minus the maximum to the minimum, so you will get 2 times this one is mega, and then R is 10K. 10K is this one is 10. This one is the answer. So 18 microvolt. Okay, so hopefully all of you get the answer. And then okay, that one is about the power. This is the power. There is KTB, and then voltage noise. Voltage noise is power noise is KTB. Voltage noise is 4R V square equal to 4R KTB. So this one is more into the other measurement. So we have the noise figure, noise factor, and SNR. Okay, noise figure and noise factor are measures of degradation of the signal to noise ratio caused by component in a signal change. It is a number by which the performance of an amplifier or a radio receiver can be specified, with lower values indicating better performance. So signal to noise, okay, this SNR, signal to noise ratio is to measure the degradation, or this one is to measure the performance of the system. Okay, and then it's also calculate how much noise imposed in the system. So the equation for SNR equal to 10 log S. Okay, SNR, another equation is equal to S over N, where S is the signal and N is the power. And S is the signal power and N is the noise power. Okay, so SNR is S over N, but in dB you will use 10 log S over N. So signal power over noise power. And okay, so the lower value indicating better performance. And then for the noise factor, will this mean this is the signal power over noise power, so it actually SNR input over SNR output. So the noise factor is an SNR input over SNR output. So the equation is equal to SI over NI over SO over NO. And then the another parameter is noise figure. Noise figure is the difference in decibel between the noise output of the actual receiver to the noise output of the noise output. Okay, so the equation for noise figure is 10 log F. This F is equal to this. 10 log SNRI over SNRO, or it's equal to, because for dB, when it is divided, it's equal minus. When it's multiple, it's plus. So maybe some of you confuse F and F. So for the F, so for the factor, noise factor F is like this, and then for the noise figure NF is log. So this means figure have G, so the equation have also have G log. So you can remember like that. So in the noise calculation in the amplifier, okay, to simplify the analysis, in the following model is used. That is the amplifier with noise. So usually the system it's model that system have amplifier and it has input and output. So this is the input and this is the output, and Ni is the noise at the input, and Os is the noise at the output. And there also have noise in amplifier, we call it Na. So and also have gain. Gain is okay, we also have gain here. And then some of the, this means some of its model like this. That means some the internal, this means the amplifier noise is take out, so it become Ne. It's put outside, it put at the input, so it's become, it have Ni and Ne, noise input, and this is Ne take from actually from the amplifier and it's take out. So the equation is No equal G and I and A. So if the amplifier, if the noise in the amplifier is only at that noise, but the noise from the input multiplied by the G, so it's become G and I. But the noise in the amplifier only use that. But if it's from the outside of the amplifier, so it's become N-I-G plus N-E-G. So also can write as G multiplied by Ni plus Ne. So this is the equation for the noise amplifier. So yeah, this Ne come from here. Ne also same as Na over G, and Pn, power noise, is equal to noise at the input is equal to KTIB. So I is equal to input. So it's based on KTB before this. Okay, for this one, okay, please try this equation first. Is example first. Have you get the equation from this? Okay, just jot down this equation first and then try that example. Okay, what parameter or what is what parameter that is given in this equation, in this example?
Doctor,
Yes.
we use what formula for this question?
Uh, you use this okay, for this one, use okay, for okay, we discuss. Okay, firstly, what given in this equation is this is the bandwidth B, and then input noise power of 0.082 P. Okay, this is same like this. So this is actually the amplifier input noise power. Okay, okay, so we have NO and I and NE here. So this is the value of NE, same as this one. So before this, the equation is okay. We have this one for the okay. We have this formula to show the model of amplifier that is from NA to NE, and then it's given here only the how to change the NI and E. But the equation before this asks about the noise factor and noise figure. So for the equation for noise factor is SI over NI uh, over SO over NO. Okay, here. Okay. The equation you want noise factor and noise figure. Okay. What is the formula for noise factor? Can someone of you share with us what is the formula for noise factor?
SI over NI
SI over NI
over SO over NO.
over SO over NO. Okay,
Yes.
and then what is the formula for noise power?
To which one, Doctor? KTIB? Is that?
Yes, KTB. KTB is the
Oh,
formula of noise power. Okay, so here we have the B here, and then here for the equation we have T. This is the T. Okay, and we have an I, an E, and O. So actually this is an E, and okay, this question is not uh, not one the N O. It's only one the F. F and after this an F. So for the F, we have SI over NI, SO over NO. But the this equation not mention about the S, about the signal. So F equal SI over NI and SO over NO. So it's become okay when we have S. Okay, we assume that S is same. So it's become in because it's bottom and it's go up. It's become like this. So F equal NO over NI. Okay, but NO from before this is Okay, this is the formula for NO. Okay, this is the formula for NO. G and I plus this one. But for G, okay, we this means is equal Ni plus Ne. So we need to measure the Ni first. Ni is KTB. K is 300. Sorry. K is okay, T is 300. K is 1.38 times power of negative 23, and P is 5 times 10 power of 6. So you will get the N. Okay, it's like this.
Doctor,
Yes.
why do we assume that the S is the same for input and output?
Um, because in this question, it's not given the S value, so it's only give the parameter to for the noise power. So that's why we just use the given parameter to calculate the noise factor. So for the given parameter is only have the N, O, and Ni. So that's why we use that this one. We use the F equal to Ni plus Ne over Ni, like this. It depend on question. Some question is given about the aspect. Some of it only give the like this question. So you need to calculate the noise power from the source input. So this is the K, T, and B. So this is the Ni. Ni you got is 0.021, and then the Ne is given 0.082. So because both of this is pico, so it's because pico and pico is can cancel each other, so we get the noise factor is 4.9, and then the noise figure and F is 10 log F. So you will get the the answer is 6.9 dB. Okay, please try for this B. Use the same method to solve this answer, this question.
Doctor,
Yes.
for for N output, the equation is not G
Yes.
N1 plus NE.
Yeah, because before this we have G, but G is the okay. G is the gain of that amplifier, but because G also not given in these questions, what we can how about it? Okay, try to use this first. I will explain about that in the next class. for the why we cancel out the G. Use this method first to solve the B questions. For the reason of S and G is cancelled out, inshallah I will explain in the next class. Okay, what you got for the noise factor for the B? Any of you have the answer? Shakira or Azra? Dida Fadila, you got 11. 1.1 1.19. You use the same method. Okay, this is the answer. It's wrong, Dida Fadila. Also, Shafika also wrong. Okay, any of you? Okay, I'm not sure why you get the wrong answer. Please try again to get this answer. Actually, it is same method as before, just change the temperature. So it's change the Ni. Okay, I hope you get the right answer and know where you got wrong in the calculation. I proceed. We also only have 10 minutes. Okay, how many of you have class after this? So, all of you not have class after this? So, how many of you have class after this? Because it actually is for 6 like more, but it's more on calculation, so it takes time. Can I proceed even more after 10? Please respond.
Yes, Doctor.
Yes.
No, I don't
Okay.
have class, doctor.
Okay. So most of you not have class yet until 10. So I just proceed. I'm not sure, maybe until 10 something. So I just proceed first. So previously we learned about the amplifier noise. That means we have the noise input, noise of the amplifier, and noise output. So we can calculate the noise factor, noise figure, and so on. So that's one is only one amplifier. But how about if we have many component? This means many component in parallel, in series, in cascade. So in communication system, cascaded connection is commonly used. Below is the example of cascaded connection. So we have, for example, we have antenna here, and antenna receive the signal. We have the input signal, input noise, and input temperature, and it's go into the amplifier, preamplifier, and this preamplifier also have the NE, the noise of the amplifier here, and then the amplifier have the noise factor and also have the external temperature one, and then it have okay, this S1 is the input of this system, but output of this preamplifier. Okay, it's go on with this is the input of that system and output of the system. Okay, this is the cascade connection. So okay, so we need to divide this connection into several part. Okay, for the first part, we measure at this part first. So it's become, we only take the SI, NI, TI, GI, NEI, and G1, NEI, F1, and TEI. Okay, in the communication system, okay, before this, for the previous lecture, I only mentions about the signal. We have signal, it's been input into the communication, into the system. But today, I introduce you about the noise. This means for every system, other than signal itself, noise also interfere in the system. So we have a signal and noise. Okay, for the okay, this is the amplifier, and amplifier has gain. That means it amplify the signal. If the signal is small, and then is emphasize the signal to max. This means it's amplifying the signal, and it's bigger. So the output of the signal, the output of this preamplifier is S1, and the equation to get the output signal is gain multiplied by S1. Okay, that is for the signal. And then for the noise, as the equation is G1, for this the equation is G and I plus NE. But this one is NI is the output. It is same of the output from this system. So NI or NO is equal to G1 times NI plus NEI. NEI. Okay, this is NEI. Okay, NE1. Sorry, NEY. NE1. Okay, so when the equation is like this, and then N is the noise power. It is equal to KTB. And this T, okay, for Ni, the T is referred to Ti. But for NE1, the T is referred to TE1. Okay, the equation become like this. And we can simplify into KTG1KB Ti plus TE1. Okay, this is the equation to get the noise here, N1. Okay, that one, okay, this is the first level. And then we go to the second level. Okay, in the debonded letter here, we have F2, G2, and TE. And the input is S1 and N1, and the output is S2 and 2. Okay. For the same like this, the output signal is the input signal multiplied by the gain. But here, this is S1. The input is S1. So the S1 is, you put this equation into this. So this is the S2. Okay. And then for N2 here, the noise here is G2, because this is the G2. And 1 is the input, and NE2 is the amplifier, this means amplifier noise. So the equation is G2 multiplied by N1 plus NE2. Okay, and then we have N1 here, and N1 is equal to this. So this N1 you put into this one. So the okay. Yeah, okay. Firstly, it use this one, G1 and I plus NE. And then it's expand. So when you expand, when you grouping, so you will get this one. Okay, so second, settle for level 2, and we reach at the level 3. Okay, level 3 here we have G3, F3, and TE3. Okay, and same like before, the output signal is G gain multiplied by input signal S2. And then for the S2, the equation is G1, G2, Si. So you will get this G1, G2, G3, Si. And then for the noise, same like before, G multiplied by N2 is the input, and NE3 is the amplifier noise. So after you expand it, put the previous equation, you will get this equation. Okay. So F is the noise figure total. Okay, we have the original input signal here and the output signal here, and the noise output here and the noise input here. Actually, the F is equal SI over NI by SO over NO. Right, this is the equation, right? So, right, for NO and SO, it's have, okay, and also NI is, okay, NI is simple like this, but NO is SO, and okay, SO you will get this, and NO you will get this one. Okay, and because it have the same here SI and SI, you can cancel it. So you will get the equation of F total is like this. But when you, okay, when you take out this one, okay, take out this one, and because G1, okay, this one you can cancel out, K also can cancel out, so it's become, maybe also can cancel out. Okay, it's become T1 plus TE1 over TI. Okay, this is for the first part, second part, and third part. So it's become like this. Okay, so this is the equation for F total. But for the another equation is F equal to TE over TI. F equal TE over TI. So it's become, this is F1, F2 plus 1 over G plus F3 minus, F2 minus 1 over G, F3, let me see. Okay, for the F equal to 1 plus TE over TI. And then F total is F1 plus F2 minus 1 over G1 plus F3 minus 1 over G1, G2. Okay, because this one, okay, we have F here. We have F1 here, F2 here, and also F3 here. And also we have G1, G2, and G3. Okay, we can simplify the longest equation before into this equation. That is F total equal to F1 plus F2 minus 1 over G1 minus F plus F3 minus 1 over G1 G2. Okay, you also can use this one. This is the simplify of this long equation. Okay, and this equation, this F1 plus something that is equal is called as Friis formula. Okay, Friis formula is F total equal to F1 plus F2 minus 1 over G plus F3 minus 1 over G1, G2, and so on. So the equation is, the first is only F, and then this one is Fn minus 1, the n here. Okay, this is the equation for the Friis formula. And as before is F equal 1 plus TE over TI. You also can write as TE equal F minus 1 multiplied by TI. So the TE total the total noise temperature is TE1 plus TE2 over G1 plus TE3 over G1 G2 and so on. Okay, and this formula is work in linear. So values, for example, S and R, F that use the log need to convert to linear. So for example, if it's given 10 log dB, it's equal to 10 dB is equal to 10 logs P P. So you need to change it, go to there. So log P equal to 10 over 10 P is shift log. Shift log also same as 10 power of that one. So that one is 1. So you need to change from dB into the linear. Linear means no dB. And to change it, you need to shift log it. Okay. Okay, this is the last example. This is the last example. Please try it first and then we will end this class. Okay, which equation that you need to use for this question? Okay, for the temperature, what equation that you need to use to get the antenna temperature Ti? Dida Fadila? Or Nur Johan?
Doctor, I'm not sure. Should we use the equation in the freeze formula?
That one you will use to get the noise factor. But for the temperature, you need to use the G G multiplied by NI plus NE first. Because in the N is the KTB, and for the NI you will use TI, and for the NE you will use the TE there, because it's given the NO here. So NO you can use NO equal G and I plus NE, and then G N is KTB plus KTB, but this one is KTI and this is KTE. So you already have the tens micro here, already have the 10, it's here the gain, and K is 1.38 times of negative 93. Also you already have all this, only the TI. So you solve this and you can get the TI first. Okay, anyone get the TI?
600.
Hmm?
600 Kelvin.
Pardon?
600.
Okay, yes, correct. Faridah Sahdan. Okay, proceed with the, so the TI is 600 Kelvin. So for the F, the noise factor, you can use the formula of 1 plus TE over TI here. This you can use this formula. F equal to 1 plus TE over TI. What you got for the F? Okay, anyone get the value of TF? Value of
1.2.
pardon?
1.2.
1.2.
2.
1.2. Yes,
2.
1.2. Okay. Good. Farida and Atira. So is the solution. So how you get the TI value, and then the F. Okay, for the F, you can use the F equal to 1 plus T E over TI, or F equal NI plus NE over NI, and you should get the same answer. Okay, any problem until this, for this question, for first, second, and third question? Okay, no. So you already reached the last slide. So what you have learned today, you have learned about the definition of noise, type of noise, Johnson formula of the noise, or Johnson-Nyquist formula. Johnson-Nyquist formula is the P equal to KTB, and then voltage formula for the noise is V squared equal to 4R KTB, and signal to noise ratio is signal noise over signal power over noise power, and then noise factor is SNR input over SNR output, and then noise figure is 10 log noise factor, 10 log F, And then the freeze formula. Freeze formula is the last one. This is the freeze formula. F total equal to F1 plus F2 minus 1 over G1 plus F3 minus 1 over G1 G2. And also this one, F equal 1 plus TE over TI. And also TE equal F minus 1 multiplied by TI. Okay, this 3 is the freeze formula. So, okay, that's all for today. Any questions? Any question for today?